Well, good morning, everyone. I'm Rick Fienberg, the press officer of the American Astronomical Society, and we're coming to you today from the Hilton San Diego Bayfront, where it is the week of our 228th AAS meeting. This morning's briefing is about the latest news from the Laser Interferometric Gravitational Wave Observatory, and we're very excited to be able to bring that to you from here. Please, if you are in the audience, silence your cell phones. So the way press conferences work at the AAS is I'll give a brief introduction, I'll introduce all three of our presenters, then I'll turn it over to them. They'll speak in turn, and when they're finished, we'll open it to questions and answers. We also have a very large webcast audience this morning. If you're a journalist tuned into the webcast and you received the password to get into the chat room, you'll use the chat room to ask questions of our presenters. Well, last year, 2015, was the United Nations sanctioned International Year of Light. And one of the rationales for that was the centennial, the 100th anniversary of Einstein's general theory of relativity. And it was interesting that one of the last great predictions of Einstein's theory of general relativity was that there should be gravitational waves, undulations of space-time. And it was during the centennial of his theory and his prediction that they were detected for the first time. And that, of course, led to the biggest news of 2016 so far in astronomy and physics. And today we're privileged to have the next greatest news, the next biggest news. We have three speakers. They're all from the LIGO and Virgo collaborations. First, you'll hear from Gabriela González. She's the LIGO Scientific Collaboration spokesperson, and she's based at Louisiana State University. Then we'll hear from Fulvio Ricci. He's the Virgo spokesperson, Virgo, of course, being the European Gravitational Wave Observatory. He's at the University of Rome Sapienza and INFN Rome, and that's the acronym for the Italian National Institute of Nuclear Physics. And then we'll finally hear from Dave Reitze from Caltech. He's the executive director of LIGO, again, the Laser Interferometric Gravitational Wave Observatory. All right, with that, I will turn it over to Gabriela, and we'll get started.
Well, thank you, Rick. And I want to begin thanking the AAS for hosting us, for announcing this news. It's an honor to be here talking about how on December 26th of last year at 3:38 UTC, you might notice that was Christmas evening in the US, gravitational waves from black holes were detected again. We told you about the announcement in September 14 of gravitational waves detected in September 14. We did it again in December. These gravitational waves were also produced by the coalescence of two black holes 1.4 billion light years away, and in traveling that long distance, these gravitational waves produce a very tiny change in space-time when they travel through the Earth. These gravitational waves had a peak amplitude that would change the distances by 3 parts in 10 to the 22. That's very, very small. That's like changing the distance between the Earth and the Sun by a fraction of an atomic diameter. And despite these being so tiny, these LIGO instruments on Earth detected very clearly these gravitational waves. It takes a lot of people, physics, and engineering to build these exquisite instruments that were funded by the National Science Foundation almost 40 years ago. And they detected these gravitational waves very clearly. We are very proud of this being the beginning of gravitational wave astronomy, and we are very proud of the O in LIGO. That's because we are now a real observatory. That's why also we're so happy to be at the American Astronomical Society meeting. So these black holes, like I said, were produced by the coalescence of two black holes. These were smaller than in the first detection. One had 14 solar masses, the other had 8 solar masses. They merged at a higher frequency, so we could see the last almost 30 orbits of the dance of these black holes. That led us a lot more information than we had before, and I will tell you a little bit more about that. So again, the masses were 14 and 8 solar masses. They merged into a final black hole with 21 solar masses, emitting 1 solar mass of energy. Now, you might remember that for the first detection, when we looked at the data suitably filtered, you could see the first last cycles before the merger and then the ring down. Here, you don't. If you look at the red trace on the left and the blue trace, the red trace on the left and the blue trace on the right, you don't see this gravitational wave. You might think you see it because we have plotted the waveform that we found on top of it, but you don't see it by eye. But that's not how we look for these gravitational waves. Fulvio will give you a lot more details, but the way we look for and find these gravitational waves is trying to correlate a lot of templates of what we expect in there and seeing whether the template matches our data. And these templates that we plotted here for Hanford and here for Livingston, they are the same template for the coalescence of two black holes, produced what we call a signal-to-noise ratio, that when the template is correlated with the data at a random time, it produces a number that's a small number and it's a random number. But when the template matches the data at the right time, and with the right template, then you get a peak, and we call that a signal-to-noise ratio. And this is why we say that we clearly detected this gravitational wave, because we can clearly see this peak with a signal-to-noise ratio of 11 in Hanford and 8 in Livingston. It's not because you see the signal by eye in the time series, it's because you see it in the signal-to-noise ratio. But then you have to answer, how often do you see just by chance? So you have to know the background of your instrument. And here we show a plot, a histogram, that shows 2 ways of calculating the background of our instrument after we have taken the first detection out of the data. And this is the signal-to-noise ratio. This is the one detection that we found with this loudness that has the 2 signal-to-noise ratios combined, and you can see that it is much, much higher than the expected background. This is what we call 5 sigma. This detection has a significance larger than 5 sigma, and that's why we say we have detected another gravitational wave. I'm very proud of that. Now, you also may remember that we like to show these gravitational waves decomposed in frequency. So this is the signal frequency versus time. Each pixel in here shows what is the amplitude of the signal at that time, at that frequency, on the left for the Hanford detector, on the right for the Livingston detector. And for the first detection that was so loud, you could see a fraction of a second trace in here that increased in frequency in both detectors. For this signal, you can't. You don't see almost anything in Livingston. You might think you see something, but in Hanford, you see a faint trace. Now, what's important about this, and what was not so obvious before, is that we could see this template for a whole second in our data. It entered our frequency band at 35 hertz, it merged at 450 hertz, it spent a whole second in the data, and that again gives us a lot of information about the signal. And when we do this analysis, we can also play it. We can also convert it into sound. And we do this first with the filtered data, but with the raw data, if you want, without changing the frequencies. And when you do that, you don't hear, for this detection, or even for the first detection, the chirp that you might have heard in YouTube. For that one, what we did was shift it in frequency a bit higher so you could hear it better. But here I'm going to have you listen to the chirps, first from this detection, that is a second long, then for the first detection that was much shorter, first at the natural pitch, that is what the data shows us, and that's low frequency, so you will hear thumps, but please notice how much longer the thump is for this December detection. And then we'll hear it again, more pleasant to the eye, shifted by 400 hertz at higher frequencies. So let me play it for you. This is what we call gravity's music. So this is a natural pitch. So this is a long one, and this is a shorter one. And now for the increased pitch. It's much easier to sing at these frequencies, although I don't sing. So this is what we saw. We had a second detection. On December 25th in the US, Christmas evening, we detected confidently another gravitational wave in the LIGO detectors from black holes. This was produced by the coalescence of black holes with 14 and 8 solar masses each, merging into a black hole with 21 solar masses, emitting an energy of another solar mass. This all happening 1.5 billion years ago, 1.5 billion light years away. With this, we can tell you now the era of gravitational wave astronomy has begun. So now we will hear from Fulvio about everything that we saw when searching for black holes in 01, which wasn't just this second detection, and then we'll hear from Dave about the future of the field. Fulvio?
I have to wait just a couple of minutes. Now I am ready. So let me start by saying that I am very happy to be here. I look a bit more tired because I am just arrived yesterday night from Europe, and I will leave tomorrow. But I cannot miss this occasion, which is the occasion for the announcement of the second detection. So. And by the way, I have also to add that I am very happy to be hosted by the American Astronomical Society for this announcement. Let's start. Gabriela has focused the presentation on the second event. I will try to give you an overview of the results concerning our hunting on gravitational waves, in particular for which concerns the black hole mergers. The data that we collected during 01 were the data which are related to this period of time, which goes from September 2015 to January 2016. The coincident time is approximately of the order of 51 days, and when we apply the sanity checks and data quality checks on the data, we reduce this amount of data just covering roughly 39 days. What we are doing, mainly what we are doing is to look at this kind of signal. The signal is now has been shown several times in occasion of the first detection, but let me summarize the structure of the signal. In practice, there are three parts. The first part, which is the in spiral, it corresponds to the phase in which the two compact bodies are approaching. Then there is the peak. The peak of the waveform is the moment in which we have the merger. And then the third part, which is the moment in which we have just one body. The final configuration of our system is just one body, which is relaxing. And so it's like a bell, the sound of the bell, which now is going to zero. We are hunting such a kind of signal, and this signal, as Gabriela said, typically is hidden in the noise. If you have to apply a specific technique, an algorithm, for extracting the information of the existence of this signal from the data, from the output of the interferometer. What we do is something well known by the expert of radar. This, the matched filter was developed last century, and what we are doing is a well-known technique for, and is applied in several other contests. Let me show here this movie. We are starting by doing an hypothesis on the existence of this signal, and then we correlate this existence to the output of our detector. And if the signal is present in the output of the detector, you see the output of our correlator on the bottom of this figure, and you see the huge peak that is our alarm, is what Gabriela said before, give us the information concerning the signal-to-noise ratio that we have in the case of the detection. This is our procedure, and the results are summarized in this plot. We got 3 triggers. We got 3 significant triggers. The 2 of them are those that has been presented, the trigger of September 2015. Then there is the Christmas event, Christmas for the American people, so for the European was not anymore Christmas. And then we have also a third candidate. Let me call it candidate, and it's better called it trigger. Why I am speaking in this way? Because typically the 2 signal that detected in September and the other one which is detected in December are a very high signal-to-noise ratio, 24 and 13, and a very high statistical significance. Typically, when we speak about a detection of 5 sigma, typically this is granted as something that is sure. No discussion about the existence of the signal. In the third case, the statistical significance is lower. We have a signal-to-noise ratio which is lower, so we don't flag it as a gravitational wave signal. We call it in a different way. We call it LVT, which means LIGO Virgo trigger, and this is relatively significant if we interpret it as an astrophysical signal. Still is a signal which is coming from the merger of 2 stellar black holes. On this plot you can see in more quantitative way why I am speaking about statistical significance. This is a plot similar to that Gabriela was shown. There are the 2 clear events, September and December, and then you see that the third one, the LVT event, is in a dangerous situation. It's not far from the black line, which is the representation of the background. So this implies that we are less confident on this third event. Here there are the characteristics of the 3 events. These are plots where you have the strain on the vertical axis, and on the horizontal axis there is the time, and you see the difference of the 3 events. On top you have the first event, the event of September. It's short in time, higher amplitude, and then on the bottom you have the December event, which is very, very long in time, but its amplitude is smaller, it's not so intense, and you have seen it also in the presentation of Gabi. And then the third one is in intermediate situation. It's not so long as the event at the bottom, and this amplitude is less to the respect of the first one. These are the 3 events, and let me show this artistic view of the masses of the black hole. This is a very nice picture done by the expert of graphics of Caltech. Very nice picture. You have here on the vertical axis, you have the masses of the events. Here on the left side, there are the black holes which are being identified on the base of X-ray observations. So these are the results of the astronomical observation. And there are now also the black holes detected by LIGO. We added also the third one, but on top of the third one, we have to put a question mark on top of it because of the less statistical significance. So I conclude my presentation by saying that this is a clear indication that we have an evidence for a population of stellar mass binary black holes in our galaxy. This is the beginning of a gravitational wave astronomy. And this is just, I repeat, it's just the beginning. We did the first time, as Dave is likes to say, we did it, and now we did it again, and we will do in the future. And for the future, I think that we have to wait the presentation of Dave, that he will explain what will happen in the future. Thank you.
Well, good morning, everyone. I, too, am delighted to be here talking about gravitational wave astronomy at an astronomy conference. Usually we go to physics conferences. I have the fun job of talking about the future. And I think one of the things that's clear from the first two discoveries, and even possibly three discoveries that we made, is that the future is going to be full of binary black hole mergers for LIGO. We're going to see a lot more of these as we go forward. What I want to do is talk a little bit about where we think the field is going to go in the next 5 to 10 years. And we'll start early on next year and we'll move forward. So we concluded our first observing run, what we call the 01 run, just this last January. And we saw these three events. And right now, the LIGO detectors are not operational. We are, in fact, in a dark phase where we're improving their sensitivities. When we designed these detectors, we knew we wouldn't be operating them right out of the gate at full sensitivity, that it would take time to be able to get them to full sensitivity. So our first run, the run where we detected these binary black hole mergers, we were operating about 40% sensitivity. And that graph you see on the right-hand side of the screen there, it's complicated, but I just want to point out a few things. First, it shows the spectrum by which gravitational waves are detectable by LIGO. And it goes from about 10 hertz to a few kilohertz. On the y-axis is the thing we try and detect. It's the gravitational wave strain, this delta L over L. And the point here is that lower on the curve is better. So as we go forward in time, we'll go from the cyan curve, which is about where we were in the first observing run last year, into the green curve, which is where we hope to be in the next run, which will start in September of this year. And then further progress down to those two solid lines, which is where we get to our design sensitivity, probably sometime in 2018 or 2019. Now our goals for the second observing run is to improve our detector sensitivity by about 15 to 25%. That may not sound like much, but what's important to realize here is that sensitivity is a direct measurement of how far we can see a particular gravitational wave event, a binary black hole merger, for example. And since we increase the distance by which we see an event by improving our sensitivity, we increase the volume by the cube of that number. So even a modest 25% improvement in sensitivity, and by the way, it's very hard to get that. These are very temperamental detectors. It gives us a factor of 2 in event rate. So you can do the math for yourself. We saw 2 or 3 events in 4 months run that we had with the first observing run. We're going to be running for 6 months for our second run, and we'll see more of these. Whether we see 6 or 8 depends on what the true rate is, and we'll learn more as we go. Let me now talk about the special role that Virgo will play when it comes online. So Virgo is a detector much like LIGO. In fact, technologically, it's almost equivalent to LIGO. It's located in Italy. They too do projections for their how they're going to be progressing in their sensitivity as a function of time. Their first run will commence with our second run, and so they'll start probably, I think, in January or February of 2017. It's not completely defined yet, but we are confident, or pretty confident, that they'll be running with LIGO in our second observing run. So why is this important? Why do we need Virgo, and why do we in fact need a network of gravitational wave detectors? Well, I'll tell you that in the next slide, but let me just point out that in addition to the 2 LIGO detectors and Virgo, we also have a detector that's under construction by colleagues of ours in Japan that's called the Kagra detector, which will be running at the end of this decade. And then we've recently gotten permission by the Indian government and funding by the Indian government to put an identical clone of the interferometers that we have at Hanford and Livingston into India. So we have this, not just 3 detectors, the 2 LIGO and Virgo detectors, but hopefully 5 detectors going forward into the next decade. India will be operating in 2023 or 2024. All right, so why do you need 5 detectors? Well, it helps to be able to see the event more confidently when you see more detectors, but that's not what this is really all about. What it's really all about is finding out where the events came from, all right? You don't want to just know that we saw black holes. We don't want to just know the masses. We want to know where on the sky they came from, and this is where the astronomy hook really comes in here, and this is why we're happy to be here. I want to tell you a little bit about the grand goal of this going forward. All right, an interferometer turns out to be a pretty poor telescope in the sense that it can't actually localize events. It's more like a microphone. All right, so how do you localize gravitational wave events? Well, you use multiple interferometers, much like you would triangulate. Your cell phone gets triangulated on cell towers. Turns out that 3 interferometers is necessary to get some good positional information, and you'll see how good later on. 4 is better and 5 is better. So that's why we need all of these gravitational wave detectors. But so what? Why do we want to actually be able to see an event just with gravitational waves? We also want to see it with other kinds of astronomical telescopes. So this is another kind of source that we hope to see at the center of this plot here. It's a binary neutron star merger. And unlike black holes, which are pure space-time, we don't expect that when black holes merge together, they produce light. We do expect when 2 neutron stars collide together, they're going to produce a lot of light. And the reason why is they're made of matter, they're made of neutrons. Now these neutron stars aren't as, they don't radiate as effectively as black holes do because they're not as massive, but they do the same kind of dance where they orbit around one another and collide. And when they collide, they should not only produce gravitational waves because of the nature of their orbits, they should produce gamma rays, X-rays, optical, infrared, and even radio waves, and even neutrinos perhaps. We don't know yet because we haven't seen all these things at the same time. So the goal is to use all of these different messengers, photons, gravitational waves, neutrinos, to be able to say more about the event that we're looking for. So now let me tell you the challenge. The challenge is that gravitational wave detectors are very poor localizers of gravitational wave events. So this is how well we did in LIGO with the 2 events and the 1 low significant event that Fulvio talked about. You put yourself in the center of this sphere here, the Milky Way is projected on it, and those 3 events, all right, represent the best that we can do with our 2 LIGO detectors for pinpointing, and I'm using that word loosely here, the signal, where the signal came from. The outer contours are the 90% confidence level. And if you're an astronomer in the room, you know, when astronomers look at that, they go, you know, that's not really well localized. So we need to do better, and we can do better. So now I'm going to show you the same plot, but I'm going to do it with using simulated Virgo data, using the sensitivities that we expect in 002, the second observing run, and also the two LIGO detectors. And you can see, well, we're not still great, but we're doing very well. In particular, on the first event, the September 14th event, we've gone from something that's about 250 square degrees, which is basically about 1,000 times the angle subtended by the moon, to something that's much, much smaller, about 20 times smaller. And so now people who do transient astronomy, you know, they can cover that whole area in a night and try and see the optical signatures here. So we can do a lot better in the future, and that's where we're really trying to go. So I'm going to wrap up now with the last slide, which is basically my view of the I'm a detector scientist. My view of the gravitational wave network, and these are detectors that will be operational in the coming decade. India, as I said, is on the drawing board. So what you're seeing there is an engineering drawing that's been done in India. But we think this is tremendously exciting. You're going to be hearing more from us as we go forward. Certainly we're going to be seeing a lot more black holes, but hopefully binary neutron stars, if we're lucky, perhaps a supernova. So the message I want to sort of close on is gravitational wave astronomy is real. We're here. Thank you.
Well, thank you all very much. You know, it's really a privilege to be in this room and at this meeting this week because, you know, we're literally standing at the dawn of a new era in astronomy and physics. I'm not quite as old as I look, but I can remember, you know, when planets were fuzzy little disks, and then thanks to the space age, they became real worlds, and we've seen up close the moons of the outer planets, and we've opened our view from visible light to include infrared and radio and X-ray and gamma ray and all the rest. And now we're detecting gravitational waves. So it's truly a remarkable moment, a truly historic moment. It's a privilege for us to be able to be here today. I would like to, before we turn it over to questions, I want to thank a few people. Well, first of all, I want to, of course, thank our three presenters and the institutions that they represent. Putting an event like this together takes a lot of effort from a lot of people, and I want to give a shout out not just to the LIGO and Virgo collaborations and the LIGO scientific collaboration, but also to Whitney Clavin here from Caltech. She helped organize things with me. Chrissa Cuvelioto, one of our vice presidents over here, she was the one who invited Gabby Gonzalez to give the Kavli Foundation lecture, which she'll be doing at 11:40 this morning. I want to thank the NSF for funding LIGO and giving us this amazing new tool. Jim Olestad, are you here? Yep, very good. Okay, so Jim represents NSF. And I think it's really poetic almost that the International Year of Light came to a close with Einstein giving us a Christmas present, right? Einstein's Christmas present. Okay, we're going to begin with questions here in the room. Remember to wait for the microphone. My trusty assistant over here, Eric, has the microphone. Please identify yourself by name and affiliation and tell us who you're addressing your question to. And then if you're on the webcast, please queue up your questions via the text chat. All right, so we'll start here.
Hi, it's Chris Crockett from Science News. First of all, congratulations. Fantastic. This question is to whoever feels like answering it. Could we use what we do know about the masses and spins of both detections now to try and learn something about the formation scenarios for the binary system or the environments in which they live?
Well, I should mention that there are several other LIGO colleagues here, some a lot more expert on this, like Vicky Calogra. But let me tell you that the one thing that we could do with this event that we couldn't before, because of the length of the waveform in the data, is to get an estimate of the spin of the black holes before merging. And we can tell that one of the black holes was spinning, which is not obvious, was spinning with at least a dimensionless number of 0.2. We measured the spin with a dimensionless number between 0, not spinning, and 1, which is maximally spinning. This one was at least 0.2. We can also measure the spin of the final black hole, but we expect that black hole to have a spin. We don't know about the original black holes. And that's astrophysical information that informs the scenarios. We cannot yet tell. There are different scenarios for how black holes are formed, and I think with these two events we cannot just yet have enough information to distinguish between different scenarios, but that's what we expect to do with more detections. The informations that we need are the chirp masses, which are well measured. And again, we have 2 data points from these 2 detections, the spins of the black holes before merging, and we expect to have more information about that from future ones. But again, there are several scenarios. We cannot just distinguish those, but that's one of the science targets.
Yeah. And if I say something wrong, Vicky will correct me, but the more of these things we detect, the better we'll start to get a handle on some possible mechanism for formation if it picks one formation mechanism, dynamical capture over, binary formation or something like that. But we do. I think with 2 detections, we're not quite there yet.
I should point out that in our 2:15 p.m. press conference, one of our speakers will be talking about exactly this issue. How do you create pairs of black holes like the ones that LIGO is beginning to see? Okay, other questions? We have one over here.
Hi, my name is Gaurav. I represent Astrobytes. First of all, congratulations. My question is, what does the collaboration think about the fact that you started off your discoveries with 3 black hole mergers and not seen any other scenario? Is the opinion, is that serendipity, or is that something physical vis-a-vis the rates of these events per year?
Well, do you want to say something?
No, by the way, in principle, we should not be surprised, because before the detection, we had a couple of papers and internal notes that were stating that the probability, the highest probability, was for black hole mergers for the O1. Let me say that we were at the threshold of our predictions. So, in a certain sense, the surprise is in the fact that now we got it. But it's not a contradiction to the respect of what we wrote in papers before that.
Let me add a bit more to that. I think we were surprised, I think it's fair to say. But the predictions for binary black holes, like Fulvio says, there were some predictions that we would see those. There were others that said we wouldn't at all. So the predictions went from 0 to many, and we saw 2. So now we can narrow down that. I don't think we expected to see, we were not quite prepared to see this, and we scrambled to put it all together and do the analysis as well as we did. But we expect to see other systems in the future, like binary neutron stars.
I think in the diagram that you showed, Dave, with the sensitivities as the detectors are improved, those lower curves were down in the realm of neutron star mergers, right? But the upper ones where we are now weren't really quite there yet.
Yeah, the uncertainty in binary black hole merger rates was orders of magnitude, I think 3 orders of magnitude. And the important thing to point out here too is as we get to the point where we're touching the sensitivity curves that we designed these instruments to be at, again, there's uncertainty in the rates even with these 2 detections, but we could be seeing 1 binary black hole merger per day, all right, or maybe 1 every 2 days. We don't know, and we'll learn more as we go forward, but we're going to be seeing lots and lots of those events. We're not giving up on binary neutron stars.
Not at all.
Those are really important, and those are, I think that's going to be another next big thing that we see here.
And if I can, I just want to clarify that we are presenting here the results of our search of all of O1 data only for binary black hole systems. We are searching that data for lots of other systems too. We don't have expectations, but of course we have to search and we might find. So we haven't finished the analysis for binary neutron stars, for neutron star black holes, for pulsars, for stochastic background. We are still doing a lot of analysis of O1 data.
I hope I'm still the AAS press officer when we get to the point where I can say, oh, that's just another binary black hole coalescence. That's not worthy of appearing in a press conference. We'll wait for something new. Okay, we have one over here.
Hi, Chris Lintop from BBC Sky at Night. I wanted to ask about follow-up to this detection. I know that some of your, electromagnetic astronomer friends were told about this and were able to follow up. Can you say something about which observatories contributed and what you might have hoped to see?
I don't remember all of them. Maybe Gabby does. I know that Palomar Transient Factory, for example, followed up. I think Pan-STARRS followed up. Swift, X-ray telescope followed up.
Also, there are telescopes also in Europe. For sure, the telescope at ESO, LVT, was used for the follow-up, electromagnetic follow-up.
Right. Fermi also.
So Fermi also.
Yeah.
See, and now, by the way, there are also other collaborations that are looking at the archived data. the collaboration that archived data, for example, Agile, which is another satellite looking for gravitational wave signal, is looking for that.
I didn't mention this, but the news that we presented today are published, appear today in physical review letters. There's also a draft that we put online with the results of this binary black hole search, but many of our collaborators, our astronomy group collaborators that have done the follow-up, are putting out their press releases and the results. There are, from the ones that did the follow-up, there were no counterparts found. There was a supernova. There was a strange system found, but it's not a counterpart of gravitational waves. That was by pan-stars, and they have the results out already, I think.
Yeah.
So for the first one, I think there were about 25 observatories that followed up. I don't know what it was. Do you know what it was for the Boxing Day event?
It was about the same number.
Same number.
And again, we published the paper with the first detection and all of the groups that followed up. We are planning to do the same with this detection shortly.
And with 100 institutions in your collaboration and 1,000 members and 25 observatories doing follow-up searches, it's no wonder you guys can't keep a secret too well.
We do well enough.
You do pretty well. You do
Not so
pretty well,
bad,
but not perfectly. Right. Okay. Any other questions here in the room? Do we have any on the webcast? Yes. Okay. Great. So let's bring the mic over here, and we'll start taking some from online.
Okay. The first question is from Daniel Fischer from the German journal Abitur Astronomie. And this question is, was the candidate LVT 151012 known in February? And if, I'm sorry, was the candidate, the most recently announced one, known in February? And if so, why was the much worse October candidate, LVT, mentioned but not the better December candidate? That's a question for you.
Yes, we were still vetting. We were still doing the full analysis, so we hadn't finished the vetting of the December event. And in fact, when we, in December, when we had news about this trigger and we shared the news with astronomers, we had to make a decision on whether to go ahead with finishing the analysis and the release of the first detection, or whether to wait for the second one. And we decided to do them separately. We couldn't keep the news about the first detection, and we were almost done with the analysis by then. But we did know about this trigger, and we did talk. It was in our papers, it was in our talks. We knew about this October event. I mean, it is in the histograms that we published. At the time, the false alarm rate was already just as high. So it was just as little significant as it is now. But because we had this second event now, perhaps we are not as afraid to call this trigger more astrophysically, more likely to be of astrophysical nature than of noise.
Right, and we did know about the December event in February. The reason we didn't report it is because there's a pretty long chain of analyses and checks that have to be done before we are confident in saying that a gravitational wave is really, a signal trigger is really a gravitational wave signal. And we weren't ready to do that. And we're a very conservative group of scientists. The first event that we announced was really big news, and we didn't want to make a mistake. We think the second event is big news too, and we don't want to make a mistake on that one.
But in any case, we don't want to do the mistake.
Yeah, yeah. As Rick says, the next ones maybe not be as interesting.
Okay, got some more?
Next question comes from Michael Riordan, freelance. Is there any chance that further massaging of the data will improve the significance of the third candidate, LVT 151012?
No.
Or is this the best we are likely to see?
No, the analysis is concluded. I mean, the search for black hole mergers is concluded. Now the statistical evidence is now rather well defined. No chance to add other extra information on that. We have to, as a scientist, what we have to do is just to follow the typical Bayesian approach or probabilistic approach. This means that there is a probability that this is a false alarm, and so the probability that this is a signal is 1 minus the probability that is not. I mean, that's that's all. we
I
can-
suppose if
at that point, what we have to do is just to bet on it or not.
Quantitatively, this, the probability of this being from astrophysical origin is 85%, compared
not
with
bad.
the other two detections, in which it's 1 minus a part in a million.
But a year and a half from now, after you've done the second run and you've had 3 observatories going, if you have in fact managed to see a dozen or so more, you'll be able to say with more confidence whether the thing you saw in October during the first run is likely to have been real, because you may have other systems that you have stronger detections, but they're very similar in mass and frequency and so on, right? So give you some extra confidence.
Perhaps.
I am not sure that this is the right method, because typically the main problem that we have in our analysis is that we are dealing with non-stationary background of the detector. So the fact that we are running in a different situation with different detectors means that the behavior, the statistical significance is difficult to assess the statistical significance of the event taken 1 year before with detectors in different conditions. So I think that we did our best now.
Okay.
The next question comes from Seth Borenstein from Associated Press. If this is the music of the cosmos, how would you describe the soundtrack of the universe? Symphonic, blues, disco, etc.
Jazz.
Coming from Louisiana, blues.
Jazz.
Sounds like crickets, right? It chirps.
Jazz is happier here.
Jazz.
Jazz, classical music.
Hopefully not
Depends on
blues.
your feeling.
So opinion-based, I'm guessing.
Perhaps a little bit of classical music thrown in for good measure.
It's only played 2 notes so far, right?
All right, the next question comes from Miguel Krell from El Mundo in Spain. He would like to know if it is possible to detect inflationary gravitational waves in the coming decade with 5 gravitational wave detectors operating around the world.
Yeah, so LIGO, Virgo, and the 2 detectors under construction are looking at high frequency signals. We're in some sense the gamma ray detectors of gravitational waves. The signals from the inflationary universe, from the Big Bang, are very low frequency, so their wavelengths are very long. They're measured in fractions of the universe. So it's unlikely, based on standard inflation, that LIGO and Virgo will be able to detect those kinds of gravitational waves. But there are other detectors that are actively looking for them, and the hope is in the next 5 to 10 years that they will be able to see the song of the Big Bang at the beginning of the universe.
And I think the space-based gravitational wave detectors are designed to see the cosmological signal too, right?
Yeah, at some level, they can probe phase the phase transitions during electroweak symmetry breaking. But yeah, it's the LISA detectors aren't going to be up and running until what 2030, 2035. So it's going to be a while. So that's why I think the detectors like BICEP, CAC are going to be more closer to getting to that signal.
Those are all the questions we have from online.
Okay, any more here in the room? Over here in the front, Dirk? Down in the front. The farthest distance you could possibly have to run.
Hello, Dirk Lorenzen, German Public Radio. How long did it take in December to get the news out to the follow-up observers?
A day. It was a bit more than 24 hours, but I think it was about a day. I'm looking at John O'Connor here. He's closer to 2 days.
I don't remember exactly, but it might have been 2 days.
It was 2 days with the first one. It was less with the second one. So between 1 and 2 days.
The second one was less.
Yes.
So, even in Christmas. Huh?
Any other questions? All right, I'll take the chair's privilege to ask a couple myself. This might be for Gabby, but any of you can address it. Can you help us, just in the simplest terms, disentangle from the signal how you get an estimate of its distance, how long ago the black holes merged?
Well, for these systems, where we have a model for the source, then we know what astronomers would call the intrinsic luminosity, because from general relativity, we know the amplitude of the gravitational wave at the source. And from our measurement, we know the amplitude of the gravitational wave here. and the amplitude of the gravitational wave decreases like 1 over the distance, not the distance squared, but the distance. So that information tells us about the distance. It's the amplitude here and the knowledge of the amplitude at the source. That's, of course, a simplistic view.
Right,
we have to
but
use
that's basically
that,
it.
That's
Okay.
basically it.
And just to further clarify, so the frequency and the rate of change of the frequency, is that to first order telling you more about the masses?
Yes,
Okay.
and the best information we have is not about the individual masses, but about the combination of the masses that we call the chirp mass. That's what we can determine the best. And from that, we can extrapolate on the masses with a larger uncertainty, the masses of the individual black holes. But yes, as you say, it's the frequency, or the cycles of the frequency and the merged frequency what tells us about the mass.
Okay. And then finally, probably for Dave, can you describe some of the steps that you take to improve the sensitivity? Because obviously the basic structure of the observatory isn't changing much. So it's,
Right.
is it your calibration, or you're swapping out detectors, or?
Yeah, there's a number of things that have to happen. The way we'll get that 15 to 25% is mostly by just turning up the laser power. So our detector were designed to operate with a laser power of 125 watts into the interferometers. That turns out to be a lot of laser power, and we knew we couldn't operate there right off the bat. So we operated in the last run that concluded in January at about 25 watts. We're going to go up to about 50 watts, and that improves the high frequency region. It just has to do with the photon statistics and shot noise. The work to improve the low frequency region, which is the harder region to actually really make improvements on, has to do with trying to understand all of the subtle couplings. This is a very complicated device in the sense that you have two hanging mirrors. Those mirrors are free to swing around. In fact, they're designed to react to passing gravitational waves, and we try and keep all the other forces out of there. But because of the nature of the mirrors, the nature of the way they're suspended, the nature of the way they're seismically isolated, there's a lot of couplings in there, and seismic noise, for example, can compromise it. Our control systems, we have a lot of feedback control loops that keep the interferometer locked, keep the mirrors in the right positions, keep them in the right angles, and there's a lot of noise there. And there are things that we don't yet know, and that's one of the reasons we're going through this commissioning period, is that are there noises that maybe fundamental noises that we don't understand that have there's things like thermal noise, that vibrations that occur, and maybe there's just something that we don't understand there. So we know what we'll do to get to O2, to get to O3, the observing run in 2017 or 2018. We have some good ideas about what we're looking for, but I'm not ready yet to say we know exactly the path to get there. So.
Okay, good. Any other questions online? One more has come in, okay.
This comes from Kayla Cofield, and the question is,
She's from Space.com.
yes, if Gabby can clarify how they know the amplitude of the signal at the source to determine the distance.
That's from general relativity. We know how binary systems produce gravitational waves, and that's how we know about the model. And that's what's so different about knowing, having a model for the source. When we detect signals, for example, from an unknown source, a transient that we don't know what it is, even if it has an electromagnetic counterpart, if we don't have a model for that source, then all we can tell you is that it has an amplitude of 2 10 to the minus 22 or 5 10 to the minus 22 here on Earth. But that doesn't tell you about the distance unless you know what produced that system. And that's what's beautiful about this binary system, that we have general relativity predicting that.
And if you can localize future sources, both with gravitational waves and potentially by finding a counterpart, like if you can get a redshift, but you don't have a model, now you know the distance, and so you can build a model
Exactly.
that makes
Yes.
physical sense. Okay.
Yes.
Yeah. Anything else online? Nope. Anything else in the room? Okay, good. Got one more question down here.
Hi there, Tom Target from Sonoma State. Based on the improvements that you're projecting, the 15 to 20%, will you be detecting, say, neutron-star mergers, maybe at the neutron-star limit, with the same significance as you're currently detecting gravitational waves?
Yeah. It's a good question. I can't say for certain, and the reason we can't say for certain is even for binary neutron stars, of which we know these things exist, because we've seen them with pulsar timing in our galaxy. The rates are still very uncertain. So I would say that it's possible that in O2 we'll see a binary neutron star merger. It's not. I wouldn't bet on it right now. And again, because of the mass differences, the neutron stars are 1.5 solar mass, 1.4 solar masses roughly. They're not good radiators, so they have to be. We have to see them closer in. These black holes that we saw were 1.4 billion years away. The limit at which we can see binary neutron stars is about 500 million light years. So it's if there's a uniform distribution, there's just less of them in that volume. So I would be very happy to have a press conference after O2 talking about gravitational waves from binary neutron stars. We'll have to see.
Okay, one more from Chris over here.
Thank you. I wanted to go back to this measurement of the spin of one of the black holes on the way in. So the first question is whether we know the other one wasn't spinning or what limit we have on the second. And then second part of the question is to ask whether the fact that it's spinning suggests a merger origin for that incoming black hole.
Well, the answer to the second question is no. Again, it's not enough to distinguish scenarios. The answer to the first question is we don't even know which of the black holes was spinning. We only know that one of them was spinning with at least a spin of 0.2. So you have very limited information. I hope that helps.
It's matter of signal-to-noise ratio.
Yes, if we expect that with louder signals or with longer signals, we will get more information. Yes, and of course that will come with better detectors.
So having answered that question, I'll follow up my earlier question and say, what is it that you're looking at in the signal that indicates spin? Is it something about the shape of the curve, or is it something else?
Well, again, when we look when we estimate the parameters of the signal, we have lots and lots of templates, and we see which templates match better, and we have a probability. We have these cloudy plots with one point for every template, and the match to the masses and the spins and all of that. So if you have, we have these for processing systems, that is systems in which the black holes are spinning, and that produces a precession of the orbit. So our templates, in the beginning, actually when we did the first search in O1, we didn't use precessing templates because we weren't ready to do that. In this one, we did it later, and we have a paper about that out there now. In this one, we had precessing templates, so we could we could try to match these templates that had spins in there and see which one matched better. Okay. And the ones that had one black hole spinning or the other black hole spinning with 0.2 matched better than the ones with the black holes not spinning.
Very good. All right, any other questions? We're getting very close to the end of our hour. Well, if not, I'd like to thank everybody again. Thanks to you also on the webcast. Gabby will be giving a talk at 11:40 upstairs in Sapphire E, the plenary hall. So I encourage you all to go to that. And again, we have one more press conference at this meeting this afternoon at 2:15 p.m. Pacific time on black holes and gamma ray bursts. And again, one of the presenters there, Fred Razio, will be talking about models that he's creating to try to explain where these kinds of very massive stellar mass black holes might come from. So
and if I may, before you finish, here in the second row, we have a lot of the LIGO collaborators. If you can raise your hand for people who want to answer questions.
Don't wave too hard. We don't want to shake the room up, the space. Yeah.
Thank you.
Great. No, it's glad to have you here, and congratulations to all of you. As I said before, it's a privilege to be alive at an era when astronomy and physics are going in such great new directions, and we look forward to hearing many more discoveries in the months and years to come. Thanks very much.
Thank you.
Thank you. Thank you.